Good morning, and thank you for inviting me for the second time to speak at the Isaca Budapest chapter yearly conference. My name is Asaf Weisberg. I serve on the Isaca board of directors, and I am the founder and CEO of IntroSight, a cyber risk management consultancy firm providing services mainly to financial institutes, critical infrastructure, and governmental ministries. Today, I would like to share with you insights from a very interesting project that IntroSight had conducted for one of its clients, the Israel National Cyber Directorate, an agency under the Prime Minister's office which is responsible for the cyber resilience of the entire civil sector in Israel. The INCD asked IntroSight to develop on their behalf a tool that will provide guidance on how to conduct a cyber risk assessment for industrial control systems. The results of this project were a practical yet methodological tool for conducting a structured ICS cyber risk assessment and a board of directors brief on OT cyber risk management. Unfortunately, both are only available in Hebrew. Prior to this project, IntroSight had conducted a similar project for the retail sector, and so fairly early in the game, we realized that cyber risk management in the ICS arena is very unique and different from what we have seen before. ICS typically refers to building management systems, critical infrastructure, and manufacturing sectors. The principles that I will cover today apply to all three. But before we continue, allow me to introduce you to the Johari window model that was developed by two psychologists, Joseph Luft and Harrington Ingham, back in 1955. This model aims to improve self-awareness of the individual and at the same time improve a group's relationship with that individual. The Johari window is built of 4 quadrants, and its overall goal is to increase the size of the arena where collaboration is most effective. On the top left, the arena represents the area where facts are known both to the individual and to the group. On the bottom left, the hidden area represents the area where facts are known to the individual but are unknown to the group. On the top right, the blind spot represents the area where facts are known to the group but unknown to the individual. And on the bottom right, the unknown area represents the area where facts are unknown both to the individual and the group. By now you probably ask yourselves, what does he know that we don't, which makes this model relevant for today's talk? Hang on. Let's start with the basics. It is common to describe an ICS network according to the Purdue Model, which divides ICS elements into levels 0 up to 5. Where level 0 introduces the physical devices such as temperature and pressure sensors and actuators such as valves, fans, and solenoid motors. Level 1 includes intelligent devices such as the programmable logic controller, the PLC. This type of hardware reads information from sensors and operates actuators according to pre-configured logic rules. Level 2 includes control systems, which are responsible for supervising, monitoring, and controlling the process. Among them, you can find the SCADA system and the HMI, the human-machine interface. I recommend reading this Isaca publication to learn more about ICS network elements. It is called Industrial and Control Systems, a primer for the rest of us. To get a better understanding on the ICS network elements, let's take a look at the following schematic example. So, we are now the control engineers facing the following task. Ensure that the water temperature in a circulation pipe does not exceed the set point of 70 degrees Celsius. We will first program the PLC using the engineering workstation to read the water temperature from the sensor. We then set the following rule. While water temperature is about 70 degrees Celsius, fan is on. The PLC will now continuously read the temperature from the sensor, and when the temperature will exceed 70 degrees, it will instruct the fan to kick in. When the temperature reading goes under 65 degrees, for example, the PLC will instruct the fan to shut down. Throughout the process, temperature readings and the fan status are continuously sent to the SCADA and HMI systems for monitoring and logging purposes. If you'd like to see how this might look like in the real world, then this is a possible view of those elements. In this example, the PLC acts as a thermostat. It performs an action based on the temperature that it reads from the sensor. In other cases, a PLC may be connected in parallel to more than one sensor, for example, to a pressure or flow speed sensor, and instruct other actuators based on these pre-configured programming. Back to the INCD project. While starting gathering information, we have interviewed professionals from various industries and critical infrastructure sectors and found out that there are two significant players in the ICS cyber arena: control engineers and CISOs. And pretty quickly, it became clear to us that there is a thing going on. So before we continue any further, let's get to know these two players. The control engineers are highly knowledgeable with ICS processes and systems, highly committed to process reliability. They have strong understanding of the potential consequences should something go wrong. On the other hand, they lack awareness to potential cyber risks, have little knowledge with cybersecurity risk management disciplines, and available products and solutions for risk mitigation. The CISO, on the other hand, usually has little knowledge on and understanding with ICS processes and systems, lacks understanding of the potential consequences should something go wrong, and but on the other hand, has high awareness to potential cyber risks and a solid knowledge with cybersecurity risk management disciplines and solutions. Obviously, there are other players too, but the more I've learned about the dynamics between control engineers and the CISOs, the more it resembled the Joe Harry window model, where the individual is the CISO and the group are the control engineers. Illuminating the CISO's blind spot and thus increasing the size of the arena is a good starting point for improving overall ICS cyber risk management. And to do that, let's take a closer look at the most significant difference between traditional IT and the ICS world. Let's start by analyzing the behavior of the Irongate malware, which is somewhat similar to the Stuxnet malware that was used to take out Iran's nuclear centrifuges in Natanz uranium enrichment facility. The malware attacks the PLC and then sends commands to the boiler to raise temperature. Malware reports back to the SCADA and the HMI systems, temperature is okay. The result? Temperature is above normal, while the HMI is blind to this change. Let's see how this might look like in real life. We see the temperature rise within the boiler and steam starts to leak out. Not a pretty sight, is it? If to be precise, the impact of data leakage is very different than oil or gas leakage. Try also to imagine a scenario of changing the ingredients and the doses mixture in the food or pharmaceutical industries. So the first lesson for the CISO is very simple. Safety and reliability comes first. In the OT world, it is common to see CIA, confidentiality, integrity, and availability being spelled AIC, where availability comes first. I would like to suggest a more comprehensive view of OT consequences, as can be found on NIST's Cybersecurity Framework Manufacturing Profile, which is based on NIST framework. The manufacturing profile relates to business objectives, which I prefer to call categories of consequences. And as you can see, they are maintain human safety, maintain environmental safety, maintain quality of product, maintain production goals, and maintain trade secrets. If we take a closer look, maintain trade secrets is similar to confidentiality, maintain quality of product is somewhat similar to data integrity, and maintain production goals resembles availability. The left two items are unique to ICS, human safety and environmental safety. And the CISO has to remember these parameters while considering other risks as well. While the CISO has to learn more about ICS, he has a lot to offer to improve cybersecurity risk management. Remember the Purdue Model? The Purdue Model is a theoretical model representing functional levels and not network architecture. The first thing we need to acknowledge is that a typical ICS network is 10 to 30 years old, and that both its architecture and devices were not developed with security in mind. Back in the days, OT networks were truly isolated and used proprietary and unsecured protocols, which are not routable over the internet. Today, almost every ICS network is connected to the IT network, and proprietary protocols are encapsulated into TCP, and thus allowing them to be routable and accessible from the internet. When we started looking into network architectures during the project that we conducted, we realized that connectivity between the OT and the IT network is not built on security best practices and introduces a significant attack vector on ICS. Let's see how network architecture might look like if the CISO would apply security best practices to ICS networks. The best way to start thinking about secure ICS network architecture is by flipping the coin. Consider the operational network as the internal network and the business, or if you wish, the IT network, as the external network. Perhaps not as a public external network like the internet, but still external. The rest will fall into place because it's quite natural to how we do security. In this example, please consider the dotted red lines as firewalls which allow to block undesired network traffic. So, since we don't want to allow the ERP system with direct access to the operation network, but we do want information from the production floor to flow back to the ERP system, the CISO may recommend a staged push process similar to the following, where information is being sent from the PLCs to the historian, which is the logging server, and then being pushed out to a staging database on the DMZ, which in turn sends it to the ERP system. So we achieve the basic task of sending information from the production floor to the ERP system, but we do not allow access from the business network to the operational network. The same rule of no direct access also applies when a control engineer needs remote access to components on the operational network. For this scenario, the CISO may suggest the following stage process, where an engineer uses his workstation to connect to a gateway on the DMZ. The engineer has to authenticate once again on the gateway, and only the gateway has access on the firewall rules to the operational network. So again, we provide the control engineer with access to the production network without having any of the firewall rules providing direct access from the business network to the operational network. While applying security best practices to the ICS network, this architecture also supports the goal of process reliability, as the isolated operational network is self-sufficient and will continue to function even in cases of communications failure with any of the other networks. Up until now, we're focused on enlarging the arena by illuminating the CISO's blind spot. When I met with control engineers, I found highly professional people with very high commitment for safety and reliability of processes. And thus, They strongly believe that if it ain't broken, don't fix it. Having said that, I also found out that control engineers are less familiar with the cyber risk landscape, and as a result, are less cooperative when it comes to making changes to the ICS environment, such as changes that would have to take place if we want to re-architect how the network looks like, as we discussed earlier. In order to make these changes, it is the CISO's role to introduce control engineers to the cyber risk landscape and explain why, despite all, changes must take place. One way of demonstrating it is by using the patching process as an example for changes to systems. To patch or not to patch is not the question anymore, since these days the likelihood for a cyber event to occur as a result of an attacker exploiting a known vulnerability will soon surpass the likelihood of an event to occur due to an uncontrolled change made to a system, for example, as a result of a patching process. And since making changes to ICS by applying cybersecurity controls is more of a when rather than if, building trust and collaboration among control engineers and the CISO is a must. If you've noticed, the only quadrant that we haven't touched yet is the unknown area. The area that is unknown both to the CISO and to control engineers. What does the unknown area represent? It represents the organization's undiscovered and unprotected territory, the perfect playground for an attacker, as this area is overlooked and uncontrolled. The unknown area can be illuminated if control engineers and CISOs join forces and act as one team. As we are approaching the end of this talk today, let's summarize what is really important. ICS networks are unique with their legacy components, architecture, and sensitivity to change. The CISO has to acknowledge the difference with ICS, safety first. ICS engineers have to learn more about the cyber risk landscape. Collaboration among CISOs and ICS engineers illuminates the ICS unknown arena and thus minimizing the threats from external attackers. And again, the last example that I gave, which somewhat summarizes the whole question around changes to ICS networks. The likelihood for a failure to occur due to a cyber attack reaches the likelihood due to a change in ICS. I would like to thank you all for joining me today on this talk. I will be happy to take questions, and I hope to see you sometime soon, face to face and not on this virtual platform. Thank you very much.